Hello, everyone. This is Marc Ballouz. I'm the president of ISSMGE and excited to start this new IITT episode. This time it's about forensic engineering. To be honest, it's my favorite. This is where you really prove you are an engineer here trying to solve the problem because the problem is there. I am so happy that we have with us renowned experts, and we're going to learn a lot, starting with myself. And I'm going to share the screen and introduce the speakers. Can you see my full screen? So with us, we have Professor David Frost from the Georgia Institute of Technology. He's the chair of TC Technical Committee 302 on Forensic Geotechnics, member of TC 105. We have with us Dr. Jeanine Engelbrecht from uh, currently working in Canada, originally from South Africa, a specialist with BGC Engineering. We have Dr. Prashanth Vangla from the Indian Institute of Technology in Delhi, member of TC 105, and Dr. Wei Li, uh, General Manager, Ground Master Construction in Taiwan. So we have a mix, young, renowned experts, professors, academicians, and from the industry. And I love that. That was the purpose with this episode. I think it's number 28. So I'm going to stop sharing. And David, the floor will be yours to start. Welcome to all, and many thanks for joining. I'm going to put myself on mute so there's no
Are you
background noise.
are you ready for me to go?
Yes, the floor is yours, David. You are probably on Dominique laptop. You need her help, probably.
I'm gonna have to. Please just give me 1 second. Dominique, for some reason it won't let me share. But is that sharing?
Can you see the slides?
All right. Can you see them now?
Yes.
Yes. Right.
I don't know
Yes.
if we should restart so we can remove the gap or
I think
the
you can just.
admin.
I think they can just edit that out.
We can edit it. I'll tell them to do so. Yeah.
All right.
All right, David, the floor is yours.
All right. Well, thank you very much, and it's a great opportunity here to participate in one of the IITT webinars being organized by President Ballouz. We have put together a series of 4 short presentations today to sort of give you an understanding of many aspects related to forensic geotechnical engineering, or TC302. Um, uh, So the motivation for forensic geotechnical engineering, let's begin with the fact when failures occur when either natural or human-induced stressors produce demand that exceeds natural or human system capacity. Stressors can range from extant conditions, such as, for example, just plain gravity, to temporary or permanent augmented conditions, which may either result from fatigue or from factors such as water, wind, temperature, and so on. System capacity is derived from geomorphological processes, or in other cases, human ingenuity in using materials and processes to yield engineered artifacts. While in most cases, capacity exceeds demand, errors, changes, and uncertainties in capacity and demand can lead to failure. Failures can be either single point events or result from cascading processes that lead to failure of an overall system. Forensic geotechnical engineering offers the opportunity to learn from these failures and to ensure more resilient systems in the future. Just a little history and purpose of TC302. It was constituted by ISSMGE in 2005 as Forensic Geotechnical Engineering, or FGE as we often say. It's involved in scientific investigations and deductions to identify the causes as well as the processes of distress in a structure or system that are attributed to geotechnical origins. Such a critical analysis will provide answers to what went wrong, when, where, why, how, and even sometimes by whom. Cases of remedied installations, particularly those which fail under or fall under public and government category, where the analysis and evaluation of adopted remedial measurements with regard to their effectiveness and economy may be subjected to judicial scrutiny, those also fall under the purview of TC302. Just a quick synopsis of some selected past activities of TC302, and these are predominantly in the form of symposia or seminars. There's a listing of them here. Also, in 2016, there was an edited volume titled Forensic Geotechnical Engineering, which was edited by Professors Rao and the previous chair of TC302, Professor Sivakumar Babu, and that was part of the Developments in Geotechnical Engineering series put on by Springer. And then there was there was also a more recent seminar put on by Professor Fumio Tatsuoka on the collapse of the Fujinuma Dam, which will in terms of ongoing activities of FGE, it is now conducting a mini symposium series on forensic geotechnical engineering for natural hazards impacts. It's going to be a series of symposia held in Asia, Europe, Africa, South America, North. And the reason we're doing a series of these is in part that natural hazards evolve differently around the world, and they also are addressed with different types of solutions around the world. And so we're ultimately interested in trying to understand from a more global perspective this scenario. These one-day symposia, typically we're holding them in conjunction with a larger conference. And each symposia has its own short proceedings of extended abstracts of the presentations made, and then there'll be a small volume from the contributions for each of those events. And when we finish the last of the 6 or 7 mini symposia, TC302 will actually put together a monograph comparing and contrasting the challenges and solution approaches from across the world. Just a bit about the ongoing and proposed mini symposia. We actually just held the first one in conjunction with Geotech Asia in Goa. We had anticipated an audience of about 40. It turned out we had 80 registered and attended, and it included speakers from government, practice, and academia. We have 3 more already scheduled for June in 2026. There'll be a half-day event in conjunction or as part of ICSMGE in Vienna. In September 26, we have an event in conjunction with the CREST conference in Cambridge, England. And then in October 26, there's an event in conjunction with the ASCE Forensic Congress in Orlando, Florida, USA. And finally, we're in discussion with folks for 2 more, which will be held in early 2027, one in South America and one in Australia. We just haven't locked down the final details of those. This is just a quick snapshot, but gives you an idea of what a typical event looks like. This is from the Geotech Asia. I think one thing that we were very happy that we were able to do is through a little bit of sponsorship from various entities, including the Geotechnical Extreme Events Reconnaissance Association and the Geosynthetic Institute, we were able to offer free registration to the participants, and I'm sure that also added to the value of the event. I want to now jump just for my last few slides to talk a little bit about resilience. And we're all familiar with curves that we often see like this, and I refer to this as a reactive resilience. We sort of are going along and we assume everything is fine, and then an event occurs and we fall into the valley, and we spend a lot of time thinking about how quickly and to what degree we recover from that valley. And you see terms here like partial resilience, full resilience, transformative resilience. All of these fall under what I call reactive resilience. And quite frankly, I feel that many times we almost accept this as the way to go. And from me personally, I'm not comfortable with that. I think resilient systems should embrace both before, during, and after considerations, and not just during or the immediate after. So in that context, resilience and forensic geotechnical engineering associated should not start here. And there's a tendency for that to happen. It really should be starting out somewhere out here, because there's a lot can happen between these 2 red lines. And I'm not putting specifically times on these, that depending on the event and the type, that could be months, it could be years, it could be decades. But there's a lot happens between these 2 vertical red lines that is critically important to understanding, in fact, our system resilience. In that context, I'm showing a green line here, and I didn't just randomly draw this, but I'm showing sort of the end result, and then I'm going to explain to you, where does this come from? Well, if we measure the degradation in this region here, we actually may quickly discover that we're no longer at a constant resilience, whether that's degradation due to changes in demand or capacity, if resilience is a representation of those, or whether it's fatigue or something like that. And so there's an importance to instrumenting and understanding what the instrumentation is telling us. Once we know that, we can also, and as we think about what the stressors are going to be, we may come and think about, we need to do some permanent adaptations. Now, we probably cannot afford to make permanent adaptations that absolutely can cover 100% of predicted events in the future. But on the other hand, there's some level of investment at which we can certainly dramatically reduce the potential impacts of events. But then the second part of it is what I call event-based temporary adaptation. And this may be where we've made a permanent adaptation, but then as we're aware of an event about to occur, we may be able to make a temporary adaptation that will further increase the resilience. And then once the event is passed, we can even remove the temporary adaptation if we like. And the end result, though, is that I believe we end up somewhere here, which in fact is a higher resilience than what we do if we just live within the reactive resilience world. And I call this predictive adaptive resilience. Now, I think there's an urgent need for predictive adaptive resilience strategies and solutions. And I'm going to do a very simple example here. Here's a very simple levee, and you can see that I'm showing that it's overtopped. However, if we had a little bit of prior knowledge, or we understood better what the likely demand was going to be, we may have come in and raised the elevation of that levee by a certain amount. And so now for the same level of event, we actually have um, some remaining resilience. In other words, we've eliminated the overtopping scenario. And on the other hand, if we learn that we're going to have an even higher event, then we may think about putting some kind of a temporary adaptation on the top. Now, the most common one that all of you probably could think about right away is sandbags, and that's something that's done very quickly in the days or in the hours before an overtopping might occur. And so that's a good example of a temporary adaptation, although it does typically create more problems because the sandbags after the event are typically contaminated, and then we have to dispose of those in landfills. So I think the idea is good, but I think we need to start to think about more temporary adaptations that don't have a legacy tail, for example, that has an environmental impact. So forensic geotechnical engineering, I think, can help guide both these permanent and temporary adaptations. Now, I'm going to use the Leaning Tower of Pisa as an exemplar of this predictive adaptive, and I can tell you that at the time the work was being done, at least explicitly, the team that led it, Mike Yamelkowski, John Berland, Carlo Vigiani, and even Jerry Leonards, were probably not using the terms or thinking explicitly predictive adaptive. But in fact, everything that they did fell into this particular scenario. And so I'm introducing it as a way here to dissect what I would call was a slowly evolving potential disaster to try and help understand the solution paths and needs. Many people think of Pisa as a geotechnical failure. In reality, I would argue that it's a compound geotechnical, structural, religious, art history, tourism, resilience event. It is not a failure. It has been monitored for its entire life, in other words, more than 800 years since it was first, the construction started, and adaptations were implemented periodically. A major adaptation was initiated in 1990 because of a concern for a superstructure collapse, not a foundation failure. It was a potential for a superstructure collapse that led to it. And the 14-member multidisciplinary body appointed to resolve it included experts in restoration, mineralogy, history of arts, archaeology, structural engineering, and geotechnical engineering. And I make that point because I think we need to recognize the importance that forensics and good forensics needs multidisciplinary, different opinions, different perspectives. I would note, however, since we're amongst geotechnical friends, it was led by geotechnical engineers, and I like to think that that's an important mantra. So a little bit of history of the tower. On the upper left is showing the actual loading of the tower, the weight of the tower. And as you can see there, and in the images on the right, it was 11. They started construction in 1178 or 73. Sorry, they built the first 4 stories, and then they stopped. And they stopped because they started to observe a lean. And in fact, they stopped for 100 years. So there was an adaptation which said no more construction. That was simply the adaptation. At that stage, they restarted. They made some adaptations in the process to try and offset the existing lean. Added another 4 of the stories, and then obviously the situation continued to get exacerbated. And so there was another second interruption for 100 years before finally they came back and put the bell tower on in the late 1300s. There were numerous
That's why, David, it's curved.
Yes,
because they were going up, they were straightening, and then it kept
absolutely.
tilting, so
Yeah.
it has a curved shape.
Yeah, and included in those adaptations, for example, they halted the construction, but they also used tapered bricks to offset the lean. They used different height steps within the tower, so for the people walking up, it didn't seem as inclined. They did excavation of the Catino at one stage because they thought that might help, and they tried lowering the groundwater. In fact, some of the latter two there had the opposite effect. They were not good interventions. This is sort of a plot matching the one from below that was put together by Professor Yamelkowski, and it's sort of showing the inclination and the lean. And so you can see that clearly things were progressing downwards, and so that's why in 1990 they closed the tower and realized that there needed to be a major intervention. This is a more detailed look at some of the movements and some of the more recent. This was over sort of the period from 1930, so the last 100 years. And on all of these various dots show times and places where people tried to do interventions. And the bottom line was anytime they tried to do a serious intervention, the tower responded. It was not happy with humans dabbling around. So let's come back and look at my resilience curve. So this is that classic resilience curve that I showed you. And we can't afford to be reactive. If nothing had been done in 1990, then, and I'm very careful to show that this is not real, because otherwise somebody will see this webinar and say, oh, David Frost said the Tower of Pisa collapsed. So it's not real. But we can't afford to be reactive. And so now come back and I'll add my predictive adaptive curve. So let's take a look at what the Tower Restoration Committee did. Well, first of all, they put a massive amount of instrumentation in there. There's just a quick synopsis here. But they literally, if somebody walked in the door at the ground level, there were instruments that were detecting that, whether they were vibrometers or whatever. And so they had an exceptional level of instrumentation to in the background as they were conducting their studies. The permanent adaptation was based on predictions, and in the interim to get to this, they did model studies, they did numerical modeling and so on. And the bottom line was they realized that removing soil from under the one side of the tower could help reduce the lean. At the same token, they were concerned, and so they had two temporary adaptations that they utilized. One was the lead weights that they put on the high side, and the second one was they actually put cables strapped around the tower at the third level in case the tower started to move. And as a last-ditch effort, they'd be able to at least put some tension in those cables and to try and pull it back. Well, needless to say, they completed the permanent adaptation. And so at that point in time, they removed both the lead weights and the cables. And if you go to there today, this is what you see. It's still leaning. It's about half a degree less than it was. But it's a predictive adaptive resilience. And even if it starts to lean again, at a worst case scenario, the feeling is that they've gained about 300 years more performance out of it before it may get back to the same condition that it was in. So, a few summary thoughts. Forensic geotechnical engineering is central to learning from past events to enhance infrastructure system resilience. Natural and human stressors will continue. We cannot afford to be reactive. We need to recognize when resilience and thus FGE should begin. We need to think about infrastructure systems that include permanent and temporary adaptations, and we need to learn now using FGE to avoid future failures. And ISSMGE TC302 has obviously an important role to play. Thank you.
Thank you, David. I am really impressed by how active you are in TC302 all over the world. And unfortunately, we missed you in Goa. I came maybe one day after you left, but
Yeah, I was. Yeah,
we'll meet again on the board.
yeah, absolutely. In
We'll
Vienna, I'll for sure see you.
in Vienna, yes. And I like your graph. Actually, I stole it with print screen. We should put between the two red lines monitoring, which will be probably an intro for the next speakers. We're hopefully covering that.
Yeah.
So thank you very much. Jeanine, I think the floor is yours.
Yes, thank you very much. In this talk, we're going to look at the role of remote sensing with a focus on satellite remote sensing in forensic geotechnical engineering. So in forensic geotechnical engineering, we're interested in identifying what happened, not only the infrastructure that were potentially damaged, but also affected areas. We are interested in reconstructing the timeline of events, looking at conditions before, during, and after the event. And all of this is in an effort to understand why a particular event occurred so that we can be more resilient or potentially proactive in the future. Now, to do this effectively, we need information on pre-disaster conditions or pre-event conditions, And then very often this is unavailable or not easily accessible. And the situation gets worse if after an event we can't quickly get to a field area to collect that in-field evidence. And this is really where satellite Earth observation plays an important role. Now, there are thousands of satellites orbiting the Earth currently, and a lot of them have the ability to collect data for Earth observation purposes. And in fact, the first images of the Earth's surface was collected in the 1970s already. So this means we've got a very large history of the Earth's surface almost anywhere on the globe that we can extract from satellite data. So the kind of information that satellites can provide is building baselines, so just establishing what the conditions were on the ground before an event even happened, detecting potentially precursors to events. So if we think about landslides, we might see an acceleration in movement of the Earth's surface before catastrophic failure, and we can piece together a timeline of events. And the big advantage of remote sensing, of course, is that these images cover potentially large areas. So we get a synoptic view of the area, not just the affected infrastructure, but the surroundings as well. We can build a time series of events, and then multi-sensor capabilities. We've got satellites that image the Earth in microwave wavelengths. Multispectral data can tell us about water coverage and vegetation health and productivity, and so on. So in this image that I have here on the screen, this is captured daily after a flood event in Vancouver in 2021. And after the flood event, we had daily satellite images that were captured that we could use to monitor the retreats of the floodwaters. And this kind of information was sent directly to our geotechnical engineer in the Disaster Management Center. And this information they could use to plan their daily field inspections to clear houses and buildings from the evacuation zone. Now, because the satellite images go potentially back to the 1980s or even the 1970s, we can start to monitor those slow creeping hazards that are creeping up on infrastructure that we might not know about before. So in this video that we have here on the screen, we can see a riverbank. And between the 1980s and today, we are tracking the slow progression of this riverbank as it encroaches on roads and railway infrastructure. And then this information, of course, we can use to identify and measure the rates of bank erosion and alert these infrastructure owners that a river might potentially be impacting that infrastructure in the near future. So that way we can be a bit more proactive about managing geotechnical hazards. This is an example from the recent Myanmar earthquake. In this case, we used synthetic aperture radar images captured before and after the event to identify where drastic changes on the Earth's surface was taking place. And we did this mostly to try and identify where there were collapsed buildings. But because we've got the synaptic coverage, we could zoom out, and here we could see the rupture zone of this fault was very clearly identified in these damage proxy maps. And then we could also use multispectral satellite data to map changes in vegetation health and productivity, or the density of vegetation. So comparing pre-earthquake vegetation to post-earthquake vegetation, we could identify where potentially co-seismic landslides were happening after that earthquake. And then, of course, focusing on high-resolution data, we can start to identify individual structures that were damaged. But this information is also very useful for additional information extraction, like identification of tension cracks, looking for signs of liquefaction. And of course, all of this information is just strengthened if we have field evidence that is collected as well. So building on what David talked about previously is, we can be very reactive if an event happens. We can analyze the satellite data to try and piece together what happened. But because the satellite data exists already, we can start to be very proactive about disaster risk management by learning from the past to inform the future. This image that we have here on the screen is a classic representation of the disaster risk management cycle, and Earth observation plays a role in all of these phases. And it starts with geotechnical hazard identification, just recognizing that a hazard might be present. The second phase is characterizing that hazard. So does it have the ability to impact infrastructure that we care about? How is it moving? Is it accelerating? And all of this leads to risk-informed decision-making. So we can plan for more resilient infrastructure in the future. We can plan for risk mitigations for existing infrastructure, and we can do ongoing monitoring and surveillance to make sure the risk profile of an area isn't changing. So the example that I want to use for all of these phases is in a technology called synthetic aperture radar interferometry, or INSAR. Now, INSAR data is derived from Earth orbiting satellites, and it allows us to measure millimeter to centimeter scale movements of the Earth's surface. And this image here on screen is an image of a landslide. And we can see the Earth is moving at relatively high velocities in this active lobe of the landslide. We are measuring movement rates of about 40 millimeters per year on the INSAR data. And because the data has been was being captured all the way back to 1914, we could potentially piece together the displacement history of this landslide. And in this case, we're measuring about 140 millimeters of movement over the 4-year period. So the INSAR data sets is really valuable for creating inventories of ground movement hazards. This example here on screen is again of a landslide that we were able to identify that we were previously completely unaware of. And this landslide then has the ability to impact a road that is going through the toe of this landslide. But there is also a reservoir. This landslide has the potential to create a landslide-generated wave. Very often, we also have pre-existing inventories of hazards. For this image here on screen, all of these black lines are existing landslide inventories from the United States Geological Survey. But in this case, we didn't know if these landslides were still active or were they dormant. In this case, we got INSAR data again, and with the INSAR data, we could identify areas that were moving at higher velocities than the surroundings. And this allowed us to characterize all of these landslides based on whether they were active or inactive. And then, of course, because these satellites have been around for a while, we can piece together the displacement history of these landslides. We can look for accelerations and decelerations in movement. And once we recognize that there are periods of acceleration or deceleration, we can try to figure out what is causing them to accelerate during certain periods. So in this example of this landslide, we could identify periods of acceleration. And here we extracted hydroclimate data, soil moisture, precipitation, snow melt. And we recognized that the periods of accelerated movement actually was corresponding to periods where it was wetter than normal. So once we recognize that a landslide speeds up when it is wetter than normal, then we can plan for mitigations, for example, dewatering of a slope. And all of this, of course, feeds into risk-informed decision-making. Once we know that a hazard is present, and we know the proximity of the infrastructure that we care about, we can start to do calculations like probability of the hazard occurring, so probability of a landslide catastrophically failing, the probability of a hazard having a spatial impact on infrastructure, and the vulnerability of the infrastructure. And that then allows us to rank and prioritize these hazards either for detailed geotechnical investigation or potentially for mitigation. So there's a couple of emerging technologies that allows us to do this quicker and faster and incorporate more Earth observation data. We already spoke about the large number of data sets that are available, but there has also been a recent change in most government policies to make data freely available and on an open access basis. And this means the cost of incorporating remote sensing into our programs are coming down quite dramatically. And then there's also advances in computer infrastructure. We have data warehouses like Google Earth Engine that allows us to take our algorithms to the data, process it online, and only download the results. So we don't have to have massive computers anymore, and we don't have to download terabytes of data. We can process all of that terabytes of data online and just download the results that we're interested in. And then the final component, of course, is advances in how we communicate hazards through technologies like mixed reality or virtual reality. So just to end it off there, there's a lot of benefits of using remote sensing data. We can establish baseline conditions. We can piece together the chronology of events. We can do ongoing monitoring for disaster response. And these rapid virtual damage assessment then allows us to help forensic teams to prioritize inspection areas by focusing on high-risk areas and areas with potential secondary impacts as well. And that's it. Happy to take any questions.
Dr. Jeanine, I have been to many conferences and many remote sensing presentations. I think this is one of the best.
Thank you.
Thank you so much. Quick question for the viewers. They're probably asking, can I do this in my region? How accessible are these satellites for remote sensing, like INSAR or others you recommend? I know some of them give free data,
yes.
but your impression.
Yeah, it depends on the satellite data that you want to use, but there's been like the USGS and the European Space Agency Copernicus constellations. They're capturing data all over the globe, and the historical records are available and it's freely accessible. So those are quite medium resolution to low resolution data sets, so it depends on your needs. But with the commercial satellite operators nowadays, you can probably get data collected almost on a daily basis. And the cost of those high resolution data sets are coming down quite dramatically as well, just because of the sheer volume of data that is available. So for any area, you can get 50 centimeter resolution data, probably for a couple of $100, depending on the extent that you want.
So the data you collected for this collection of landslides, was it for free or you had to pay to get
the raw
monitor?
data? The raw data is you can get it for free. There's obviously a cost involved with processing, whether you do it yourself or you outsource the processing. There will be a cost because it's computing time and so on, but the raw data is freely available. And there's free and open access algorithms that you can use for that processing as well. So it really doesn't have to cost a lot of money. And then there are also a lot of processed INSAR data sets that are becoming available as well, like the European Ground Motion Service has already processed INSAR data for the whole of Europe. And then NASA and the Jet Propulsion Lab has a displacement product, so already processed INSAR data available for the continental United States as well.
Hopefully, it's available for everyone around the world very soon for free. We need that. Thank you so much. Really, this complemented what David has presented. I think, Prashanth, the floor is yours.
Thank you. So I hope I hope you can see my screen.
Yeah, all is good. I like the logo in the middle.
Thank you. So, thank you for this wonderful opportunity. My talk is on deformation signals and clues from acoustic emissions for early warning and failure forensic in geotechnical engineering. This technology, we are working hard at ITT to develop such advanced and effective early warning system based on acoustic emissions. So my motivation that comes from, as you see in the geotechnical systems, that such as slopes, retaining walls, embankments are increasingly failing under climate extremes and rapid development. So as Professor David Frost mentioned, reactive approaches respond only after the visible distress, leading to major losses actually. To improve the safety and resilience, we must shift towards predictive adaptive strategies supported by advanced instrumentation that detects early warning signals and guides timely intervention. Importantly, the same monitoring systems capture critical data during and after failure, converting disaster into valuable knowledge for improving design, modeling, or future risk mitigation. This drives the need for accurate, reliable, and smart geotechnical sensing solutions. So before I go into my technology that we are working here at IIT Delhi, I would be just quickly go through the existing technology. As you see, we all of us know the extensometer, inclinometer, shape acceleration array. These are being used in most of the constructions. And however, these have their advantages as well as disadvantages. And we all know these sensors feel what is happening in the soil. But I think maybe it's time for us to listen to them actually. So if you listen, I think you may get more information than what these instruments provide us. So that's one motivation. And this motivation, it's not only just occurred recently, it was in 1981 after Koiner, where he had learned that in the soil, there could be acoustic emissions from the soil particles. The acoustic emissions are nothing but elastic waves. Typically, those range of frequency is from 20 kilohertz to maybe up to 300 kilohertz. And these are due to grain friction and particle crushing, particle collision, force break, grain cementation fracture. These all activities basically results into AE generation. So Koiner basically, uh, instead of conventional instrumentation, only that detects the displacements after they had occurred. Koiner idea was to listen to the soil for early micro crackings and failure processes. When Koiner proposed in 1981 the passive waveguide, he proposed the passive waveguide. They basically inserted a rod and tube into the soil and let it act like a stethoscope. But however, it has some limitations. Major limitation is that the attenuation of these acoustic waves that are generated by the particles, and failure plane location is unknown and may not connect to the sensor path, and highly variable response because of the soil heterogeneity. So in the 2003, Dixon et al., he proposed that we should have an active waveguide instead of passive waveguide, which can capture AE from any failure depth and no need to locate shear surface in advance, and minimal signal loss through the protected waveguide and reliable performance across diverse soil condition. Basically what it has is a tube surrounded by annular fill that could be granular fill, and the interactions between the tube and the annular fill basically results into acoustic waves that passes through this tube, and we can measure that. So this basically gives you a nice animation that helps you what is I'm talking about. When granular materials slide past on the steel or any metal surfaces, so there is a shear response that you see, as you see here. And then let me take my laser. And then similarly, you can see acoustics, parallel acoustics were generated, which passes through this metal plate. And these are lamp waves, constructive interference of body and surface waves at high frequency one. And these helps us to listen what is happening at the interface. And why this is so important, I would be happy to give you a brief idea as we move forward. So, sorry. Yeah. So these are some experimental insights that we have obtained from our laboratory studies, that when different particles of maybe granular material like angular particles or glass beads, when they shear against a steel plate or aluminum plate, what you see is these particles form a tracks on it, which means there is a ploughing taking place and sliding taking place, and these mechanisms may cause acoustics. Unlike what we have seen, like what Koiner proposed, particle-particle crushing friction can generate. Whereas in case of interface, because interface is important in the acoustic waveguide that what we have shown, the interface is going to be an important aspect because that's where the initial failure takes place in the device, which is much prior to the failure of the host soil wherever it is placed. So if you see this steel surface here on this, you see linear tracks which are formed by the angular particle, whereas with the glass beads you see some tracks are found, but not significant as you see with the angular particles. When it comes to aluminum, which is softer to the steel, you see more nonlinear tracks. So these indicates particle breakage, and because of the angularity and the ploughing mechanism that takes place interface causes different shear response as well as acoustics response, which I'm going to reveal in the subsequent slide. So if you see here, these are the single particle test experiments that we have done at IIT Delhi to look into the aspects like what actually is happening at a contact level to unfortunately my animation is not working, but however, when this particle shear against a plate, you see there could be breakage, there could be breakage and wear, and there could be particle rolling at the interface. And all these mechanisms basically results into different AE signatures. So deciphering those signatures and understanding the acoustic response is very crucial for the interpretation of these AE-based waveguide. So this is one macro response, and this is a micro response where when I say macro mechanical response, a shear box filled with the granular materials and sheared against the plate. And when you see this plot, the blue one represents the acoustics, which is present in the frequency. The white color plot basically shear response. As you see in this plot, you don't see much of acoustics that is being generated with the glass beads, whereas that is more evident from the single particle test. When a single particle shear against steel, you see there is no acoustics, but there's a shear response, which tells us not all the granular fill that we're going to use in the active waveguide may generate the acoustics. So it's important to identify that which particles, which material is going to provide acoustics emissions. And if you see here the macromechanical response of a angular particles with the same metal plate steel, you see significant acoustics are being observed around the peak, which means the particles are breaking, ploughing, rolling. So all these mechanisms are taking place. But these are happening around the peak of the shear response. From the single particle test, if you see, wherever there is a drop in the vertical displacement, or the shear force, you see acoustic spikes are noticed, which means the particles are basically the mechanisms dictates the acoustics at the interface. So again, I reiterate, the selection of material plays a significant role. Now, I guess, as you see here, this one animation, which is unrestricted single particle, where this same particle which was once placed along the direction, the major axis of this particle is along the shearing direction, so the top one, whereas the bottom one is the smaller axis of the particle is in the direction of shearing. As you see, the particle which is having longer axis in the shearing direction is undergoing more frustration, and it is causing more ploughing and eventually wearing, which is causing the more acoustic emissions, as you see here. And whereas in the particle which is rolling, it is causing very less acoustics. So from the multi-scale analysis, what we observed, that select the particles and particles properties and the continuum metal properties plays a significant role, as this slide presents. When we did the same experiments with the granular material with the smooth and the granular material with the rough, if you see with the in case of smooth, you see the acoustics is found to be around the peak, whereas when you have the rough continuum materials, steel plates, the acoustics is found to be much before the interface failure takes place in the waveguide. So which is more amazing, actually you get much early signals. So we have developed a strip-based waveguide instead of a tubular waveguide, which is typically used. Why? Because it has a higher effective area, higher bearing resistance, and in a horizontal orientation under high stresses, tube can deform. So this may not be happening in case of strip-based. And it is easy to place anywhere in the structure, maybe in the retaining wall. I'll be showing that some examples in the subsequent slide. So this is a rough plate, and this is a granular material that we found to be more effective in terms of creating the acoustic emissions when they shear against this plate. And then what we did, we have done experiments with the in the last direct shear box, placing this strip with the acoustic sensor, the piezo sensor, and the yellow color basically presents very silty sand, and the other one is angular particles, 2 to 4 mm. And if you see the angular particles which are in the bottom of this slide, so these have shown different acoustics compared to this one. We'll show you the in the subsequent slide. So if you see this silty sand, which is blue, and the angular sand, which is in the black, both of them have similar shear strength properties. Whereas when it is seen acoustic energy, spectral energy, we call calculated in E. So if you see, there is no spectral energy or acoustic emissions are noticed in the silty sand, which means not all the particles would generate acoustics. So we have to be very selective when we use this acoustics. And the next experiments that what we did, presence of water. I mean, like what actually we are interested in is that how the displacement rate affects this acoustic emissions, how the normal stress affects its acoustic emissions, and presence of water, because these are the three things which are crucial for us to understand what is happening in the system. So as you see here, when we did the direct shear test on the granular fill with the strip, this failure strength seems to be almost similar. Whereas when we calculate the spectral energy for both the cases, dry and submerged, as you see, the spectral energy is significantly reduced when the water has come into the system. So which indicates, though it is decreased, but it is not completely negligible, it is significant. But with respect to the dry, you see there is a reduction. As you see, for the case of displacement rate, for the dry and submerged, you see at 100 kPa normal stress, the red one indicates submerged, whereas the blue one indicates the dry. As you see, there is a rate of increase of acoustic emission is increasing with the increase in displacement rate. That indicates that, okay, the wall or any system that is failing at faster rate. So which is an important information that we can get from the sensor. And this, as you see, the magnitude of these blue and the red one is increasing with increasing normal stress, which tells you that we can also predict at what depth this failure is taking place, because the magnitudes of the acoustic emissions is changing rapidly. So that's one beauty. And then we have present them in the AB parameters, which basically we have fit the power plot, and we understood that how the AB parameters changing. So I have already explained how these are varying with the displacement rate and at different normal loads and under the presence of water. And then moving to an example, that a model study that we have carried out, we have done some experiments with the strip-based retaining wall, placing it at the bottom of the retaining wall here, as shown here. Height of the retaining wall is 1 meter and the width is around 0.5 meters. So we place at the bottom, and then we did a test. What we did, like we have removed the pin and allowed the wall to rotate at the bottom. And when we removed the pin, we waited for some time to like see if there is any acoustics and all. So there was no acoustics. Once we started allowing to rotate, you see there are some spikes that are noticed that indicates that there is a wall movement. So this is clear from our multi-scale analysis that yes, these sensors can be very pretty sensitive and accurate. And major conclusions, the factors like normal stress, displacement rate, and roughness increases the AE responses, whereas normal stress increases linearly, whereas displacement rate increases exponentially, and the roughness basically helps us in early detection of AE. And then what it matters is it acts as a dual purpose system. Early warning before the failure plus post failure forensic recorder, like a black box in the aeroplane. and offers monitoring and forensic clues, failure depth, displacement rate, water table effects. And also it provides low-cost, scalable alternative to traditional instruments. With this, I would like to stop my presentation with acknowledging my student who has significantly contributed to this work, and also my funding agency, co-research grant SCRB. This is what my last slide
Okay,
is.
very nice.
Listening to the
Listening
soil.
to the soils.
Yeah, listening to the soil is important, I guess.
I like that you can use it prior and after.
Yes.
Um, I really like it. And it's new to me. I don't know
Thank
for our
you.
viewers. Um, it emanates non-destructive testing of piles, even before that,
Right.
non-destructive testing of airspace shuttles, where acoustically they check for any damages during their journey in the cosmos.
True.
Thank you
Thank
so
you.
much for your
Thank you.
presentation.
Thank you, Mark.
Dr. Wei Li, you're next. The floor is yours.
Okay,
Try to catch up if you can. I would appreciate it.
okay.
Because we went a little bit overboard with time.
Will you be able to look at the screen and the slides?
Yes, yes, we can.
Okay. Oh, sorry. Okay, this is okay, right?
Yeah, perfect.
Okay. Okay. First, I'm really honored to be able to join this ITT talk. I think way before that, I think in the 2010s and 12s, I joined a lot of the, we call it ISSMGE lectures, touring everywhere. By nowadays, we have a lot of the fancy tool like Zoom. We'll be able to share our experience and not going very far or in the dangerous place I have been is Lahore in Bangladesh. So that's what we very good things we'll be able to meet in online. My talk today is short talk today is forensic investigation and retrofit lesson learned. I'm going to use 20 years old cases to introduce you or the audience a lot of some details of the forensic geotechnical engineering. This photo was taken about 24 hours after we first found out or aware of some sinking damage at the bottom of the shear tunnel at the shear tunnel construction for the Kaohsiung MRT at very depths about 30 meters. So sequence of the failure, we start when they dig at the lowest place water sump, that's the collect the rainwater for the metro tunnels, and they find out that some leaking from the bottom, and then suddenly because that was almost 30 meters down below, the water pressure is as high as about 3 kilo per cm square. So then water and also the turbulence of the sand and submerged in and fill with the sink already, the sump already. Then the tunnel with the ring segment start to collapse and also dislocated. We found out the failure of the ring segment, and also there's a underpass above the tunnel construction, and we found out that also sinking and distorted. Later on, the main cause to enlarge the damage is actually there are two watermen with 30 meters 30 centimeter in diameters, and the other one is 20 centimeters. and they were shut off, and then tap water just like a shut water gun shooting into the pit, create a very large hole like the underground like this one. So first things
Wait,
is
sorry
yeah.
to interrupt. Can you minimize the Zoom window so we don't, because it's
This one,
obstructing some of your
yeah,
presentation.
this one, right? And then let's see.
Important case history.
Oh, is that okay? I can.
Yeah,
Is that
that's
okay?
better.
Okay.
Yeah.
So this is
It's
the
scary, man.
quick. Yeah. This is a
Keep going.
quick drawing after about 1 day after the accident. So we have a small cave-in hole and the rather large one, a small cave-in hole in the north and rather large one in the south. And where the red dot is indicated the where the failure started. So this is for the red one is the settlement survey.
Can you go back, please, one
Yeah.
slide? Can you go
Yes.
back one slide? Yeah, where is the tunnel here? Which direction is the tunnel?
A tunnel is the
Is
green
it
one.
on
Green one is
the
two
Changcheng
tunnel.
Road or
What?
the two green ones?
The two green one and the sump is located. The water sump is located in between the green ones. There's a water sump that's for the we call it a
Okay.
cross pass tunnel, and then collecting the rainwater. Okay, then
All right.
this is quickly we do settlement survey to make sure the ground is not fair. The expansion of the ground failure is not expanding to anywhere else, and then we do the immediately the compensated grouting, indicating the how much grout we injected into the ground. And then we figure out that while we are doing the grouting, we still found out the ground is not stabilized. Then we figured out there must be some other issues. But when we do in Taiwan, we have done a lot of the deep excavation using slurry wall. Whenever the excavation pit has some failure signs or the damage, the direct mitigation measures is to water in the pit. So then we figured out maybe the problem is because of the water, the share of the water main shooting water into the ground, we haven't been able to stabilize the hydrostatic condition. So starting with the within the tunnel, we build up the double wall system to plug the 4 tunnels. If you look at it, we plug the 4 tunnel in this way. I'm sorry. In this way and this way and this way and this way. So plug it, and then we'll be able to maintain the hydrostatic condition. So then we start to investigate the damages. First one is at that time is 2005. The RPI, the resistivity imaging profiling method, is just started. We have a lot of the 2D cross sections. This is the colorful one is the image analysis, RIP image analysis. And the schematic drawing is Professor Kenji Ishihara draw that the failure cross section or the speculations to be able to describe the failure or the RIP image we obtain. So this is the left side is the cross section view, and the right side is longitudinal section view. Then the physical, we have to done physical investigation. We can rely on just plug the resistivity image profiling method. We do borehole investigation to see if we can reach the top of the tunnel ring segment to see, but you can tell that in the center part, we actually lost all the tunnels ring segments. Then at that time, I was doing some 3D analysis. We tried to do the 3D cross-hole RIP testing. We tried to create or develop the 3D image of the failures, and then the photo here is, and later on we dig out all the failures and then try to compare to our 3D cross-hole RIP testing, and coincide very well, has a very good agreement. And then we, of course, when you do the after you investigate the failures, then first thing you have to review is design. When we start for all the manual, doing grouting manual, you always have the circular or the circle representing how the grouting performance, and then you design for overlapping, maybe 2 overlapping, 3 overlapping, or only 1 overlapping. But in the reality, this is the real scale verification testing we have done with the Maida company in the test pit. Actually, when you encounter some special soil, your grout is not really like columns or the circular piles standing in underground. Maybe it's like Christmas tree. So the overlapping maybe has some fissures or the cracks. So at that time, Professor Ishihara and I were thinking about how we can test the soil, or how we can characterize the soil. Especially we found out it's non-plastic CLT sand. So first, Professor Ishihara started the pinhole test. Then I figured out that's 30 meters underground. So we have to do some pressure. We have to create enable the pressure to the pinhole test to be operated during the high pressure. So we kind of like developed the flexible wall pinhole test to really test the erodibility of this sand under 3 kilogram per center square. The lucky thing is when we start, if you have the big scale failure like this, it's a government projects, and then you be able to spend all kind of money to dig out all the remainings. After we finalized the permanent retrofit method, we decided to excavate everything down to see the failures. So if you look at the top left, it's the actual performance of the grouting for 3 meters large in diameters grouting under 30 meters deep soil. And also we found out the order where the failure started, the water sump was filled with debris and the soils. And then we also found the steel doors we closed that when the failure started, but it didn't make it didn't perform well. And then we be able to understand the failure of entire cross pass tunnels and also the ring segment damage. So then I think that's the most exciting part is when we started the retrofit works. All the retrofit works to save the infrastructure or the structure from the failure will be totally different from the design work. We always when we learn the design from university or college courses, we design nothing from the we design nothing from the scratch. But for the failure retrofit, you have to design to consider the interface between the existing tunnels. You have to protect those, and you have to also think about new tunnel construction is within the limited ground or space, and then you have to connect them together to get the deal with the interfaces for the existing and the new tunnels. And also you have to think about how can we accelerate the backfill. So we introduce also at that time the controlled low strength material CLSM as well. So this is the retrofit work that to secure the existing tunnel. We're using the ground freezing method, and we actually using the existing underground pads to be a pumping station for the freezing agents. This is the freezing method securing the ring segments, and this is the assembly of the new the new tunnel underground. For the new tunnel, for the new tunnel, we reconstructed to replace the damaged one. You see where this place also this place is very difficult to compact or even to fill. So later on, this is a view we start using the CLSM to fill it. We call it flowable fill. It can actually free flowing and fill up all the space. And then this is the after retrofit, after the tunnel is in construction and in place, and then fill up to the ground surface. So lesson learned. I think for 20 years, I have done all the forensic and investigation of different kind of failures. There's a common point of most failures, final stage of construction. Everybody start to get loosened up, and then always small issues linked to a serious damage. So quality controls or the one of the maybe last excavation will be, I repeat this so many times, I just become so careless. And then the failure causes, I think for geotech, especially within urban area or mostly for the slopes, groundwater is always the major factor. And the quality defect or it's a construction quality defects or less knowledge about the soil property. In this case, it's both. We don't know the grouting performance will be so challenging, and also we don't know that much about the soil erodibility of the soil on site. So most likely, when all the dredgeable factors meet together, failure occurred. Lesson learned 2. Forensic investigation, we have to develop in possible failure scenario, and then new technology. I think Jeanine described a lot of the large scale technology to observe the failures, and then also plunge is also talking about the micro scales technology to observe the failures. And this is another case for the photos. Is another case we happened in the north of Taiwan. There's a very large slope slide, and then we did some simulations and also the LiDAR scanning to recreate the failures. Detailed study on soil property, I think this is very important. We can learn soil by using the right test, and also tailor-made test program is often used in the forensic investigation. Retrofit work is we involve emergency retrofit and also permanent retrofit. I think this is the most exciting part to me, at least, is to save the failures or restore the structures. Always innovative and creative method will come out to design to resume and compensate the functions. Lastly, but not the least, the design to construction issue, constructability, well understanding the soil conditions. This is also previous case. When we look at all the photo during the excavation, or the slope toe already inclined, slope toe already exposes and be cut. So that no wonder the movement of slides has already occurred. And then with the rain water seeping in almost like 20 years or 30 years, and then the sliding surface, even with all kind of the ground anchors security, but still the slide ground anchor eroded, and then the corrosion, and then with the corrosion and also the slide surface slides developed the failures, mesh failures. So risk control and monitoring, I think this really kind of like echo the David's and Jeannine's conclusion. Risk identification, I think with all kind of technology, and we also need the expert experiences. And then also during the construction, during the operation, we need dynamic prioritization and monitoring all the risks. And then construction is always only like 3 to 5% of the life cycle of the structure. In operation, structure in operation is what we have to pay more attention to it, including using large scale monitoring technology, Jeanine just said, and more, or maybe we could commercialize or put the branch technology into practice. So this is my conclusion to this one. I think there's a couple of the references list out I have published in the past. I would like to, since I'm the last speakers, I would like to conclude the forensic geotechnical engineering is science. Albert Einstein says scientists invested that which already is. Engineers create that which has never been, but forensic geotechnical engineering is the state of the art, fusing science and engineering. Thank you.
Wei, thank you so much. You helped me say the conclusions. Thank you to all of you. This has been a really fantastic session with David starting about the TC302 on forensic geotechnical engineering, and then macro with Jeanine, to micro with Prashanth, and then you, a really nice case history. We're probably going to need another 15 hours with you to understand the details of that case. But thank you so much for putting it together. I wish you all a wonderful day. And because of that Christmas tree, I wish you all Merry Christmas too. Thank you so much.
Thank you.
If you want to add anything, David, to conclude, you're welcome to. We went a bit overboard, but it was needed.
I realize we went a little bit long, all of us, but that being said, I think there was a very nice message came through the sequence of talks, showing that forensics is about before, about after, about macro, about micro, and then a lot of very careful work during the actual investigation to understand what happens. So I think you got a very good picture of what TC302 is about.
And I really appreciate your work and efforts, and wish you all the best. Ciao, ciao.
Thank you.
Thank you.
Thank you. Thanks a lot for this opportunity. Bye-bye.